Good morning, Professor. We are Team 19. I'm Jolene. The problem statement that we are tackling is on speaker verification, where we determine if a given audio sample belongs to the same speaker. We'll be using binary classification for this task. For example, we'll compare speaker ID 1272 with this audio sample to see if the sample belongs to the same speaker. The benchmark we'll be comparing against is based on Prof. Xiao's paper and is reported to have an equal error rate of 4.59% on that dataset. It is achieved using a state-of-the-art E-kappa TDNN deep learning model. Deep learning models are more complex. They require extensive data and computational resources. Our focus, however, is on classical ML. And as the lower EER, the better, our objective is to match or score lower than the benchmark. To gain a clearer understanding of the task, let's proceed with the demo.
I am enrolling my voice now. So I'll write my name and I'll start recording my voice. The sky is blue. Life is full of surprises. Now I've recorded all the sentences and I will submit the enrollment. I will now validate my voice. I'll get a random sentence. The sun is shining bright. Okay, now I'll validate my voice. And the authentication is successful.
Now I'll pretend to be Tiara and then record my own voice. The sun is shining bright. Then I'll validate. So based on the system verification process, it is verified that I'm not Tiara.
I love coffee. Authentication failed.
I will call you later.
Now I will try to validate my voice again. Life is full of surprises. And it's successful.
Thank you, Jolene, for the demo. I am Nicholas and now I'll be talking about feature extraction and data preprocessing. So for initial dataset, we use the Libri speech dataset, which is the same as the benchmark used. The three key files from the dataset are enroll audio files, trial audio files, and the trials data frame. So an example of how the trials data frame will look like will be on the right below. So it has three columns, the independent variables being the speaker ID, utterance ID, and the label which states whether the sample belongs to the same speaker or not. So for feature extraction, as it comes in WAV audio file format, we have to extract its embeddings in order to process them in the classical machine learning models. So we use two methods for embedding extraction. First will be the voice print embeddings, which extracts the speaker's unique vocal characteristics. Second one will be tacotron, which is the prosody embeddings. Although the voice print embeddings alone are sufficient, prosody embeddings are included based on research that it can further improve accuracy. So for data pre-processing, after extracting the embeddings, we then combine the speaker embeddings from the enroll folder. Each speaker ID has multiple audio files. We combine their embeddings and average the embeddings of each speaker ID to create a representative speaker identity that can be easily compared with the audio samples. So for example, if speaker ID 1272 has 3 audio files in enroll, this will be combined to just 1272. Next, for data splitting, we split it into 3 different sets. The train set, which has 28,000 samples, and the speakers and audio are distinct from the test set to prevent data leakage. Validation set has 1.5k samples, and this will be used for hyperparameter tuning. The test set has 21k samples. The reason we did not follow the conventional 70-15-15 split is because we want to use the same test set as the benchmark for fair comparison. Now I'll be passing my time to Tiara. Thank you.
Hi, I'm Tiara. Upon exploring further, we realized that the voice print embeddings have 192 dimensions and prosody has 128. Since they are high dimensional, we decided to explore ways to feature engineer the data to make it more interpretable for ML models. We used UMAP to reduce them to 2D space to better understand the data. We observed that there are 29 distinct clusters, and given that there are 29 speakers, we can assume that each cluster corresponds to a speaker. There are also large gaps between clusters, indicating the speakers are distinguishable from one another. With this information, we can move on to our feature engineering process to further enhance the speaker differentiation. We first compute the scalar product and difference between the speaker embedding and utterance embedding. These calculations measure the similarity and difference between two embeddings. We use scalar values to reduce noise and make the features more interpretable as compared to its vector form. These calculations are applied to both prosody and voice print embeddings. Secondly, we further quantify the differences by computing the Manhattan distance between the speaker and utterance embeddings. We evaluated several distance metrics, and Manhattan proved to be the best. The below table shows how the data looks like after two feature engineering methods.
My name is Munir. As for the third feature engineering method, we use HTB scan to cluster the embeddings. This binary feature verifies on whether the utterance ID belongs to the same cluster as the speaker ID. We first reduce the speaker embeddings dimensions to 2D, then cluster the data using HTB scan, ensuring each speaker ID is associated with a single cluster. We then transform each utterance ID sample using the same UMAP and assign it to the nearest cluster. If the utterance ID falls within the speaker's dominant cluster, it gets a cluster match score of 1, else 0. This is then repeated for the other datasets. As for the rationale, we use UMAP because it separates the speaker clusters better than PCA, as seen here. We use HTB scan because there are some utterance IDs that do not belong to any speaker, and we will not want it to be falsely classified with another speaker cluster. Also, HTB scan handles noise more effectively than DB scan. And lastly, there is no data leakage as clusters only use the speaker ID data within that dataset, and utterance IDs are assigned afterwards without influencing the clusters. Next, we normalized our data by applying fit transform on the training set and transform on the validation and test sets. We also realized that with normalization, it accelerated certain processes downstream, such as SVM Bayesian search. We then conducted correlation analysis and found low multicollinearity with independent variables and strong correlation with the dependent variable. Now, I'll pass my time on to Jackson. Thank you.
Thank you, Munir. So after feature engineering, we proceed to model training. First, we train a baseline model and evaluate the initial performance. Second, we then optimize the model with Bayes grid search. And lastly, we train the model with optimized hyperparameter and then we evaluate the performance. Now the reason why we use Bayes grid search is because it explores the hyperparameter efficiently instead of exhausting all combination. Now the three models we use are logistic regression, XGBoost, and SVM. We use log regression as a baseline, XGBoost for its gradient boosting capabilities, and SVM for its strong decision boundaries. Logistic regression proved to be the worst performing models with 8.37% EER, while SVM proved to be the best performing model. XGBoost was the most balanced with good EER and fast computational speed. However, to remind you that the objective was to maximize the performance of the benchmark. So in this sense, SVM fulfilled this objective the best. Now exploring further, we generate DET curves for each model to better understand their performance. Now we see the XVM, the blue curve, consistently lies below the other curve. Now this means that SVM is the most effective at balancing the trade-off between false positive and false negatives across all thresholds. Hence, it is the best model for this task. We also generated a sharp diagram which shows how much impact each feature had against the model prediction. Now the Manhattan distance feature had the greatest impact throughout, while the prosody feature had the least. This aligns with our correlation analysis earlier, and in conclusion, we successfully outperformed the benchmark by 23%, and in the future, we like to argument the data with noise as we believe it could further enhance the model's robustness in real-world scenario. Now this is all for our presentation. Thank you.